Welcome to The Explainer. Today, we're going to dig into a really fascinating scientific paper that claims to solve a solar anomaly that's been bugging scientists for decades. And it does it by proposing a totally new model of physics to answer a very simple but, well, very stubborn question.
And here it is. This is the central puzzle, the real head scratcher. When the sun spits out that stream of particles we call the solar wind, the tiny super lightweight electrons actually move slower than the much heavier protons. Now, that is the exact opposite of what you'd expect. And honestly, for decades, it's been a genuine mystery.
Okay, so let's dive right in. To really wrap our heads around why this is such a big deal, we need to look at the specific things we've observed that, according to this paper, just don't seem to fit with what we think we know.
Okay, so this is where things get really weird. Basic physics, right? It tells us that if you push on a light object and a heavy object with the same force, the light one's going to take off faster. I mean, an electron is almost 2,000 times lighter than a proton, yet it gets accelerated less. And if that wasn't strange enough, the electrons get yanked around by magnetic fields, while the protons just seem to cruise right on by. It's a set of observations that seems to fly in the face of simple logic.
So you might be wondering, how do our current models explain this? Well, that's a great question. Before the paper presents its own radical solution, it first takes a hard look at why the two main models in physics, it believes, just can't make sense of this strange behavior. So first up, we've got the standard model of particle physics. The paper's argument is that this model is built on a beautiful foundation of symmetry, equal and opposite charges. But because of that very symmetry, it just doesn't have a tool in its toolbox to explain why these two particles would behave so differently. In fact, if you follow its rules, it predicts the exact opposite of what we see. That little lightweight electron should be moving way faster. All right, so what about the other big contender, the plasma or electrical model? Well, the paper argues this one runs into some serious roadblocks too. For example, if the sun is acting like a giant positive terminal or anode, it should be pulling in negative electrons, right? Not blasting them out across the solar system. And the model also seems to struggle to explain why Earth's magnetosphere pushes away all the incoming particles, both positive and negative. And this, right here, gets to the absolute heart of the author's critique. See, when you dig into some of the official explanations for, say, why the solar wind plasma doesn't just mix with Earth's plasma, the answer you sometimes get boils down to physical reasons. Now, for the author of this paper, that is not an explanation. It doesn't tell you why. It's just a label. And that gap, that search for the why, is exactly what this new theory tries to fill. So, if the main models don't quite work, what's left? Well, this is where the paper throws a real curveball. It proposes a third option. And I'll admit, it's an alternative one. It introduces a brand new fundamental force and a mechanism it calls the charge field. Now, what's really wild about this idea is its definition. This so-called charge field isn't some abstract thing like gravity. No, in this theory, it's a tangible stream of actual particles, photons, that the paper says have mass and spin. And it's supposedly emitted by all matter, it's always repulsive, and it works by simple, direct physical bombardment. I mean, think of it like a constant, invisible spray of tiny particles coming off of everything in the universe. Okay, so let's get into how this is supposed to work, because I know what you're thinking. A constant spray of particles from everything in the universe? Wouldn't that violate conservation of energy? Well, to address that, the paper proposes two key mechanics that are pretty clever. First up, there's this idea of a recycling engine. The theory goes that any spinning object, whether it's a star or even a single proton, creates a kind of low pressure zone at its poles. This sucks in those charged photons. Then it re-emits those same photons from its other surfaces, mostly around the equator. So in this view, nothing is actually losing mass over time. It's all just part of this constant cosmic recycling system. So this recycling engine creates a constant outward wind of these charged photons coming off of the sun. And that leads directly to the theory's beautifully simple, almost elegant mechanical explanation for that whole solar wind mystery. It all comes down to one thing: size. And this just nails the core idea. Imagine the charge field is like a steady downpour of rain. The proton, well, that's like a big bucket. And the electron, it's like a tiny thimble. The rain is just going to hit that bucket way more often and with a lot more total force than it'll ever hit that little thimble. The paper is basically saying it's the same thing with this photon wind. The proton is a much larger target, so it gets hammered and pushed by the wind far more than the tiny electron does. And just like that, the anomaly starts to make mechanical sense. So the theory sounds neat, right? It's a nice story. But can it do math? A theory is only really useful if it can make predictions. So the author uses this model to try and calculate something that, the paper claims, mainstream models can't do from first principles: the exact distance to Earth's magnetopause. So here is the absolute crucial point. The theory totally reframes what we call the magnetopause, that boundary where Earth's magnetic field stands up to the solar wind. In this new model, that boundary isn't fundamentally magnetic at all. It's the charge pause. It's the point in space where the repulsive push from the sun's massive charge field and the repulsive push from Earth's own charge field perfectly balance out. The magnetic stuff we see, that's just a symptom of this deeper physical boundary. And hey, if it's a real physical boundary, you should be able to calculate it. The logic here is actually pretty straightforward. The sun has a monster charge field, but it's really far away. The Earth has a much smaller one, but we're right next to it. So the math is just about finding that sweet spot, that exact point in space where the push from the sun's field and a push from Earth's field cancel each other out. And here's the answer the paper's math spits out. It calculates the charge pause to be at 11.53 Earth radii from our planet's surface. Now, what's so wild about that? Well, actual satellite data shows the real magnetopause hangs out somewhere between 10 and 12 Earth radii. This calculation lands smack dab in the middle of that observed range. Okay, a good calculation is one thing, but the real test of a powerful theory is whether it can make new predictions that we can go out and check. So, to take it a step further, the author applies the exact same logic to a different planet, Venus. Venus is the absolute perfect test case. Why? Because it has almost no magnetic field to speak of. So, according to standard models, it shouldn't really have a strong boundary to push back against the solar wind. But this theory says the boundary isn't magnetic, remember? It's created by the mass-based charge field. And since Venus has plenty of mass, it must have a boundary, and you should be able to predict where it is. So you run the exact same math. You take its mass and density, you balance it against the sun's field. And the paper predicts that the boundary for Venus, what we call its ionopause, should be found at about 7.4 Venus radii from its surface. And this, right here, is the key takeaway. This isn't just a cool idea anymore. The theory has made a concrete, falsifiable prediction. A future space mission to Venus could literally go and measure this distance and either prove the calculation right or prove it wrong. This is what makes a scientific theory, whether it's right or wrong in the end, so powerful. So whether this specific charge field theory ever becomes mainstream or not, it's just a perfect example of how science is supposed to work. It finds a problem, it critiques the old answers, it proposes a new mechanical model, and it makes predictions you can actually go out and test. Ideas like this force us to ask if our current models are the whole story, or if maybe, just maybe, there are simpler, more direct explanations for the mysteries we see in the cosmos, just waiting to be discovered.